Very good. Welcome back. Our topic today is the design of the method for maximum entropy as a tool for uh, reasoning with incomplete information. So what I want to address now is the clear problem is if you want to update from a prior probability distribution to a posterior probability distribution, it's fairly clear that what you want the posterior to do is to agree with the information you obtain, agree with whatever constraints you have. But that, in general, will not completely specify the posterior. So we need additional criteria for how do you pick the posterior. There are many possibilities agreeing with the constraints. How do you pick one? So here we go. We would like to have some general criteria, some basic strategies. One, if a method is to be useful at all, it has to be of universal applicability. And the reason is, if you're dealing with a problem with a system about which you do not know much, then if you have to pick among several methods of updating, you would not know which one to pick. After all, you do not know much about that problem. Suppose that you're dealing with, here, an example. Suppose you're doing medical trials and you decide that for medical trials you're going to use a particular method of updating. And then you're doing elections in Thailand, and for that you decide it's going to be a different method of updating. What would happen if you try to decide on a problem in which medical trials might affect elections in Thailand? Are you going to devise yet a third method? It just doesn't work. What happens if you do not know anything about the system? Which method you pick? You wouldn't know. So if the method is to be of any utility at all, it has to apply universally. So this is a very pragmatic consideration. It has to be useful. Another way to look at it is that what we're looking for is general criteria that are extremely basic and general. If it were conceivable that you could have different methods of updating, what we want to focus on here is what is it that is common to all of these methods of updating. That's what we want to formalize right now. What is in common to all of them? Presumably, what's different what would be different between different methods of updating is that, well, you're talking about different systems. The variables are different. You're talking about different kinds of information. Well, the constraints are different. But those specifics to each problem are not what we want to analyze now. We want to figure out whatever is very general and common. The second thing we want to implement in our method of entropic inference is, and this is what makes the whole approach extremely Bayesian. When you update from a prior to a posterior, there is an assumption that you have a prior. Typically, the prior is the outcome of inferences that you did yesterday or the day before. So whatever priors you're using, they are based on information that you have collected and processed in the past. And you definitely do not want to discard, to throw away information that you have collected in the past. So we would like to have a principle of parsimony, something that recognizes the value of prior information. If you collected information in the past, it is valuable. You do not want to throw it away. unless, of course, the new information makes that old information obsolete. So we would like to have a principle of minimum or minimal updating. Uh, Beliefs should be updated, but only to the minimal extent required by the new information that you have collected. So we value all the information. We're going to have to make our new beliefs compatible with the new information, but try to keep everything else the same as much as possible. Now, the other crucial principle that we want to implement here is a principle of independence. It is the recognition that statistical independence is something that is of absolute importance in any physical theory. The idea is the following. Whenever you build a model to describe a particular system, the basic idea is that you're going to include all the variables and all the pieces of information that are relevant for that system. But there is implicit this idea that everything else in the rest of the universe doesn't matter. That everything else can be ignored. The bottom line here is when you want to build a theory in physics, you want to build a theory that is actually useful and allows you to study one system without having to include the whole rest of the universe in your analysis. You want to be able to talk about something without having to talk about everything. How does this work? Well, the idea is that, well, you have a system and you have incorporated everything you thought was necessary. But of course, what happens if you were to include something else in your analysis? Well, if the something else did not matter, if it did not matter, then it should not affect your analysis. This is where notions of independence are becoming absolutely crucial. If two systems are initially thought to be independent, because their priors are independent, and you acquire information about one of them, then you initially thought they were independent, you acquire information about one, the probabilities for the other are not affected. In other words, if initially your priors were a product, independence, and you acquire information about one, then the posterior will still be a product in which the other system did not get affected. This is absolutely crucial. You do not want your updating procedure to introduce correlations that you were not aware of. You may want to introduce correlations, but if you want to do that, you have to do it explicitly. It cannot be something that your updating method does it without your permission. So what we want here is a system that says, if you believe your systems to be independent and you acquire information that is about one and about the other and says nothing about correlations, then your posterior should have no correlations. Very good. So how do we do that? Most important here, note these principles, these general criteria are not true. Truth is not something that applies to any of these things. We adopt these criteria not because they are going to allow you to match reality in any sense. We adopt this criteria because we are trying to come up with a tool for updating, and we want our tool to perform in a certain way. We want it to apply to any system, to any problem of inference. We want this tool to preserve as much as possible all the prior information that you had collected, and you want this tool not to introduce information, correlations, that we did not put in explicitly by hand. So they're not true, they are desirable. This is a matter of design. We invent this tool to perform certain functions. The tool will be deemed successful to the extent that it preserves, it works as planned, to the extent that it satisfies these various criteria. Of course, induction is always risky. You can still get nonsense. That happens. And if you start getting results that are really in disagreement with experiments, results that are empirically inadequate, then you can start thinking, have I chosen my variables right? Have I included the correct constraints? And when all of that starts failing, then you may want to come back and say, I mean, is my method for updating probabilities itself free of objection or not? In other words, the method for doing inference is also subject to experimental verification. Of course, the moment that you start having a method that sort of agrees with everything you know about inference, in the sense that it agrees with Bayesian methods of data processing, and it agrees with the laws of physics that we call statistical mechanics, and it agrees with the laws of physics we call quantum mechanics. The moment that you start having a method that can produce all of these results, then it is very, very unlikely that our method itself, our tool itself, is at fault. If you have a problem, you better figure out that you didn't include the correct information, your constraints are not correct, your variables might not be correct. There is plenty other things that you can go and tweak before you start saying, I got my expression for the entropy wrong. Very good. So what are the specific criteria? So here we go. Before that, how do we even talk about entropy? So this is where we introduce the notion of entropy. Entropy as a tool for inference. How do you update? Well, the brilliant idea of how to even approach this problem is due to skilling. Well, let me start with Shor and Johnson. Shor and Johnson realized that what you wanted was to axiomatize a method for updating. You want to go from a prior to a posterior. What Skilling realized was the following. This is in 1988. He proposed the following. The method for you to update from a prior to a posterior is best accomplished if you rank the allowed posteriors. Rank the candidate probabilities, distributions. Okay, let me see. You rank the distributions P that are candidates for posterior. What do we mean by this? The idea here is that you rank them according to preference. You put them in order. You establish in which order they are. The idea is that if, oops, P1 is preferred over P2 and P2 is preferred over P3, then P1 is preferred over P3. Now, never mind what preference here. What do we mean by preference? That we will come to in a little while. But if you manage to have a ranking, then the distribution that is the most preferred is the one that you choose. And so what is the procedure here? The ranking is implemented by a real function. So if you want to rank probability distributions and you want to say have this transitive ranking, P1 better than P2, P2 better than P3, then P1 better than P3, then it amounts to putting them on a straight line, okay? And so that straight line is what's given by, well, real numbers. So you assign to each probability distribution, you assign a real number, which we're going to call the entropy. And furthermore, since the entropy is going to, of course, since the goal is to update from a prior to a posterior, we're going to have an entropy that ranks all possible candidate posteriors P relative to the prior. So this is what gives you the ranking. And this is what we call, of course, relative entropy, and we will never use the term relative because it's redundant. All entropies are relative to some prior. Why is this idea of scaling so important? Well, the reason it's important is that this implies that you're introducing a variational principle. This is what justifies the term, the method of maximum entropy. So the idea is, among all the probability distributions that satisfy the constraint, you're going to pick the one that is most preferred, that in this ranking ranked the highest. So that is what explains maximum. You could have a minimum if you were to flip the sign of the entropy, right? But the idea is you get a variational principle. The fact that we have, why should probability distributions that you use for inference satisfy a variational principle? By design. You're designing the method in such a way that if you have a prior and you want to pick a posterior, among all possible posteriors, you pick the preferred one. Very good. This is one aspect of this. Another aspect of this that's sort of like amusing too. The entropy is real. The entropy is real for a reason. It is part of the function that the entropy is being designed to perform that you want to do a ranking. So it has to be a real number. Generalizations of S to complex numbers, vectors, matrices, blah, 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 and all that are ruled out. It makes no sense to have a generalization of entropy to complex numbers. Why? Because complex numbers do not allow you to order probability distributions. There is no order there. So it doesn't allow you to function according to this purpose. So generalizations are not allowed. Not because there is anything untrue about a complex entropy, it's just that it wouldn't work to perform the function that you're trying to design it for. Very good. So let me draw this in a picture. So what I'm going to draw is my famous statistical manifold. Here's the space of all the statistical manifold. Manifold is another word for space. This is the space of all probability distributions. Here is the prior. That's one point in this space. And now I have a constraint. Here's the constraint. The constraint is the information that allows you to say, I start with a prior and somebody or experiment or the world or whatever tells me that any one of these would be a better probability distribution. And so the problem is, as you see, that I have many here. I have to pick one. And so the way one proceeds is you rank. So these are the curves of constant S, in which I am ranking all probability distributions relative to the prior. The maximum is, of course, at this point. And here we have entropy decreasing as you go farther and farther from the maximum. So that's the direction of decreasing entropy. These are the curves here. These are the surfaces of constant entropy. And so when we get to here, you see that all of these probability distributions are being ranked. These that are closer to the prior are ranked better than those that are farther away from the prior. And what we want is we want to figure out which is the maximum. So this is the chosen posterior. It maximizes the entropy within the family of probability distributions that are specified by the information provided by the constraint. So that's what the method of maximum entropy is all about. We're gonna keep drawing this picture a few more times in this course. Very good. So now that we have figured out the basic strategy, namely you come up with a transitive ranking that is implemented by real numbers, and now we have a variational principle, the question is, what makes one probability distribution preferred over another? What makes one probability distribution be closer to the prior than some other probability distribution? What is the precise functional form of the entropy? Now we have to be a little bit more specific about the criteria. We would like them to be universal, preserve information in the priors, and we want to implement independence, right? So now, how do we do that? What are the details? So this is where the sausage gets made. It's right in the next step. So we're going to have our specific design criteria. Maybe I can actually write something here. You see, when we have propositions, the stuff that we are uncertain about, one of the things that's going to happen is that we have a lattice of propositions, and from these propositions we can construct other propositions using and or. The lattice of propositions, all the statements in your prop for that you want to talk about, the lattice of propositions is connected by disjunctions and conjunctions. And when we have this set of propositions, all of them connected by ands and ors, and we come and we sprinkle probabilities on these things, we want our probabilities to be consistent with the structure of this lattice, with or and and. The consistency of the web of beliefs is accomplished or is guaranteed. Remember, and the consistency just means if there are two ways to compute a probability distribution, the two ways have to agree. Okay, the consistency of the web of beliefs is guaranteed by sum and product rules. And the sum and product rules say the following. If you have the probability of I or J, this is going to be the probability of I plus the probability of J minus the probability of I and J. And for the product rule, we have the probability of I and J is the probability of 1 multiplied by the probability of the other, conditional on the 1. Okay, so this is what guarantees that our web of beliefs is going to be consistent, right? This is the kind of structure that we're talking about. Very good. The actual specific design criteria that we're going to come up with are design criteria that are intimately connected with these structures. We would like to have two design criteria. Design criteria 1 and design criterion 2. Both of them deal with propositions. We want in one case proposition. One will deal with propositions that are, let me write it differently. Let's see. One of these criterion will deal with propositions that are mutually exclusive. Mutually exclusive propositions. The other criterion, let's go back here. DC2 is going to deal with independent propositions. This first situation, mutually exclusive proposition, and the other, you might notice that these two both deal with correlations. Both of them deal with correlations. So this is, let me write it like this. This first one, mutually exclusive propositions, are highly correlated propositions. If you have two mutually exclusive propositions, if one turns out to be true, the other one is necessarily false. So knowing the truth of one tells you totally the truth of the other, correct? So these are highly correlated propositions. On the other hand, in this case, independent propositions, these are totally uncorrelated propositions. They're independent. What that means is that knowing that one is true tells you absolutely nothing about whether the other one is true as well. So I hope you start seeing where I'm coming from here. What I'm trying to do is take the full spectrum of propositions according to correlation, and I'm going to say something about those that are highly correlated and something about the others that are highly uncorrelated. And in the hope is that by having the two extremes more or less under control, one has a nice interpolation between the two. To the extent that I do this properly, and I do that properly, the wish is that the interpolation is unique. And we're going to see that that is indeed the case. So we're going to deal with mutually exclusive propositions. They turn out to be correlated. And notice also that when you have mutually exclusive propositions, the sum rule simplifies. The sum rule becomes very simple. While when you have independent propositions, the product rule is the one that gets very simplified. So this is kind of nice because it tells you that the criteria that we're going to use in order to figure out what is entropy functional that gives you the ranking, that the criterion is going to be like very, very, very connected to the basic rules for how we actually assign probabilities in a web of belief. So let us be a little bit more explicit now, and I'm going to write down what it is that our first criterion is. This criterion refers to the locality of mutually exclusive subdomains. It's a long name, but what it basically says is that probabilities that are conditioned on one subdomain are unaffected by information on another non-overlapping subdomain. Let me draw what it is I want we're trying to imply by this. Suppose that we want a probability distribution. And this is what the subdomain, the domain of all x's belong in some space capital X. So here is coordinate 1, here is coordinate 2, and the space X is the space x1, x2, right? So this here, this could be X is some position in 2 dimensions. As you can see, we can have as many dimensions as you want, but that's the basic idea. And so now imagine that I give you information about a domain here. This is domain D1. And what I'm saying then is that probabilities that are conditioned on this other subdomain are unaffected. Information about the one makes no difference, has no effect on the probabilities of the x's conditional on D. So what this means is that the posterior probability conditioned on D here, this is where we get information, new information on D1. The posterior probability matches the prior conditional probability. So this is what our DC1 means, the first design criterion. Interesting. Look at what I'm doing when I'm doing something like this. I'm not telling you what to change. I gave you information, but I'm not telling you what it is that you're supposed to change. I'm not telling you how to update these probabilities here or anywhere. What I am telling you is what not to update. The design criteria tells us what not to update. This is one of these features that is actually, from a pragmatic point of view, extremely valuable, because remember how when you update from priors to posteriors, there's always the problem that the prior might have been a little bit objective because you needed to make judgments about how to choose the prior, and so there is a subjectivity involved in priors. Priors always a little bit subjective, but you update presumably on the basis of very objective information. So the posteriors tend to be more objective than the priors. We want probability distributions that are more and more objective, because presumably if the information you had was good, being objective and will take you closer to better probability distribution. Very good. So what this design criterion is telling you is not telling you how to update, it's telling you what not to update. And from the point of objectivity, this is actually valuable, because if I were to tell you how to change something, you could always say, why do you change this way and not the other way? But here, I'm telling you what not to update. While there are many ways to specify how something changes, there is a unique way of remaining the same. So if my design criteria tell you what not to change, then you're closer to having a single rule that will be of universal applicability. Very good. That's it. Do not update. So what can we get from this? Well, let me write down the consequence of this. The consequence, in the next class, we're going to deal with the proofs of these design criteria. The consequence of this is that whatever entropy you have, and I'm writing it here in the case of discrete probability distributions, is going to be a sum over all the i's, all the propositions, and there's going to be a function that depends on the prior and the posterior. So if you read what I've written here, this entropy is going to be a function of a whole probability distribution. It's a functional. What I have said here is that the form of the entropy is a sum over all the propositions in your system. One way to say this is that non-overlapping domains contribute additively to the entropy. So what have we explained with this locality, the locality of non-overlapping domains? What have we explained with this design criterion? We have explained the fact that entropy is a sum over terms that each depend on one separate proposition. The propositions are not mixed within this summation here. Just add them, but each one of these functions depends on just one proposition. Comments. First comment. DC1 refers to conditional probabilities. This is crucial. Let's go back to here to see why that might be. Suppose that I give you information about this subdomain. The probability here can be affected. In fact, suppose I were to tell you that the probability here is 1. The new information tells you that the probability in D1 is actually 1. You're certain. Well, it is clear that it affects the probability here, because the moment you say that the probability is 1 here, it's going to be 0 there. So obviously it did affect them, right? But if I were to tell you that the probability here is, say, 0.9, well, the overall probability here is probably going to go down, right? But the conditional probabilities are not affected. If you have two propositions here and they were equally likely, when you give information over there, the probability of those two will be changed. But with the update, I'm arranging the update in such a way that if they were equally likely before, they will be equally likely afterwards. Conditional here, they preserve the same conditional probabilities as before. So that's the basic idea why it is that this refers to conditional probabilities. That's because the overall normalization of the subdomain can actually be changed. Second comment. Yes. What happens when the domain that you're talking about actually coincides with the whole space? This is a situation in which, remember how we phrase this? You say, if you get off your information over there, it does not affect information conditional probabilities over here. Well, if this subdomain includes everything, then what this means is that the posterior for the x, or in this, I'm using i's here, right? Yeah, I should use I. The posterior for the x on this subdomain, which is the whole space, should be equal to the prior for the whole space, or the probability should remain unchanged. In other words, if you have no probability, no information, implies no update. This is also very interesting. If you didn't acquire any information, why should you change your mind and update your probabilities? This is a sign of rationality. It's an implementation of one feature of what it means to be rational. A rational agent, an ideally rational agent, would not change its mind arbitrarily. Today I think something, for no good reason I start thinking something else. It doesn't work like that. That's not desirable. And the whole reason for this is that whatever beliefs you acquired, these beliefs were acquired in a rational way. There is no way you could revise that without reneging on your rationality of the past. So if you were rational up to now and you achieve certain beliefs, then in the absence of new information, you shouldn't change your mind. And that's a special case of this design criterion number 1. Here's another interesting one. Comment 3. Comment 3 is the realization that DC1 includes Bayesian updating as a special case. Now this is an interesting one, because it says that whatever we are accomplishing with our new method of maximum entropy, it's going to include Bayes' theorem as a special case. This is what allows us to unify Bayesian and entropic methods of inference. And the way this works is that, remember what DC1 says. DC1 says if you do not have information about the subdomain B, then you should not update. Now, Bayes' theorem refers to a situation where you have two variables. You have the propositions that you might actually measure, and you call that data, and then a parameter. And the way we handle something like this is you write this, you write this as using the product rule. That's Q again. And this is theta given I. And the update consists in writing the posterior like that, and you write your posterior as pi, and then here you have your posterior condition of theta conditional on I, and we say, okay, this is the constraint is that this guy I is either 0 or 1, depending on whether I prime is the data. I prime is the data. So the new probability distribution is going to be 0 unless you agree with the data, in which case the probability of the value I prime is 1. And for this guy here, you use the principle of minimal updating, and you say, okay, this guy did not change, like so. So what is going on here? The space, the total space that you're talking about, is a space that includes data and parameters. And what is the information that you get? You get information about a particular value I prime. This is the data. You perform the measurement, and the value of the data ended up being I prime. What does that immediately tell you? It tells you something like this. Imagine that we call this subdomain D. This is the subdomain D that consists of I prime and all the values of theta. What the information that we get is that the new probability distribution, namely the probability distribution outside here, is going to be 0 for I different from I prime. So all of these probabilities here, out here and out there, become 0, while the probabilities in this region here, those are the ones we want to figure out. So out there, it's 0. That's what the data tells us. How about in here? Well, in here, we're going to have some probability, but do we give high probability to this value of theta or to that value of theta? How do we apportion probabilities within this region? Well, we apportion probabilities with this region by saying whatever it was in the past. So you have a probability distribution there. Whatever probability distribution you had in the past, you keep it. So that's what Bayes' theorem is all about. you get information about the outside, the inside, the conditional probability inside remains unaffected. Finally, what other comment can we offer about this? Yes, if you want to figure out what happens in the continuum, you get something like this. For a continuous variable, the entropy takes then the form of a sum of this function that depends on probabilities. Sorry, I should write this as a function, right? Px, Qx. That's what it becomes. So our problem, the next problem, is to determine this function f. Our problem, the next problem, will be to determine this function f. Okay, that we do with our second criterion. The second criterion, let's go back to where we were before. At the very beginning, when we were saying we have two criteria. One dealt with mutually exclusive propositions, propositions that fall in non-overlapping subdomains. Now we want to deal with independent propositions. Basically, you have two systems and you assign a probability. The state of the two systems is given by the state of one and the state of the other. So let's go back here now. DC2 independent subsystems. This is a situation in which the states or the propositions that you're talking about can be described in terms of two states. So if these are the micro states of your system, and the system is a composite system that can be described as two separate subsystems, this describes then the microstates of system 1, microstates of system 2. And so the idea is that this is going to be an element of the whole space of propositions, which happens to be the product of the space 1 and the space 2, right? Very good. So what do we want to say under these circumstances? We want to say this is the statement of the design criterion 2. When two subsystems, are believed to be independent, and we receive independent information about two, receive independent information about the two, then it does not matter if one is included in the analysis of the other or not. This is a tricky one. The criterion that describes independence is very subtle. If your priors do not describe any correlation, when two subsystems are believed to be independent, And then we receive independent information about the two. You receive information about one, and you receive information about the other. But the information doesn't tell you anything about correlations. So you believe they were uncorrelated, and nothing in the new information says anything about correlations. Then it does not matter if one system is included in the analysis of the other or not. Another way of saying it is, it does not matter if they are treated separately or jointly. So mathematically, this means the following. If you have, for system 1, you have a prior, and you acquire information about system 1, and this updates to probability P1, and you have a prior for system 2, and then you acquire information about system 2, and this updates to P2, then when you treat the two jointly, the prior that happened to be a product updates when you have both information 1 and 2, updates to P1 and P2. In other words, the entropy was such that if the systems were not known to be correlated, the entropy itself does not introduce correlations. This is like a really, really important criterion, and the consequence of this criterion is that the entropy is updated by using a formula. If you have the discrete version, the formula is pi log pi over qi. In other words, what this does is it takes the form of the entropy, which was just a sum, and it provides you with the mathematical formula for the function f. Let me see. Let us study a couple of consequences of this. In the continuum, when you're not dealing with discrete distributions, then the form of the entropy becomes minus dx px log px over qx. This is sort of interesting because one of the things you see here is that the form of the entropy is invariant under probabilities, under changes of coordinates. This guy here is invariant under changes of coordinates. P and Q themselves, P changes by a Jacobian, Q changes by a Jacobian, and the Jacobians cancel. So this piece here is also invariant under coordinate changes. So the C2 implies that the ranking, so it implies coordinate invariant, yes, the ranking is independent of the choice of coordinates. So this is actually kind of important because after all, it shouldn't matter if you're doing your inference using Cartesian coordinates or you're doing your inference using spherical coordinates. That should, the coordinates themselves should not carry information. Very good. And I think that that is enough for today. What we are going to be doing next time is trying to be a little bit more specific about how it is that this design criteria, one for the locality of non-overlapping subdomains and the design criterion 2, the independence of subsystems, how do they lead to, first, there being a sum so that the entropy is additive over non-overlapping subdomains, and why it is that the function f takes that particular form. That is for next class. See you then.